Hello. Last time I was talking about binomial logistic regression model, right? With the help of GLM function, right? First of all, we have we have trained the model with including all these variables. I'll show you it again. I'll show you just what's the result we got first of all using all these variables, right? Let me call it logistic model 0, right? Okay, logistic model 0, GLM function y in color, I think color for all variables, data equals train, nothing may be eliminated, right? Family equals binomial, right? Okay, now summary of logistic regression underscore note, right? And I'm gonna plot it LDM underscore note. Sorry, right. Inside parentheses, let me run it and let me show you the result we got by including all these variables. I think you can remember it. So I have explained that. I think I have explained this result, right? All these results must be explained. So you can see there are some star marks over there, right? Why there are star marks? This evidence is computed with the help of probability normal standard distribution, uh, Gaussian distribution. If this is equal or less, if this is less than 2 to the power 2 times e to the power minus 16, this one means the trace up to the ideal scenario. For example, let's say that fixed acidity, right? The probability value is just 0.44 approximately, right? It says that 44% approximately, it's around 44%. With that percentage, this particular variable does not explain the model, right? So once this probability value is increased, we cannot cross this variable further, right? We cannot cross this variable further. I will explain this mathematical intuition later, but I think it's better to get an idea about how to read these more significant variables, how to read this table, and how we can use it for useful manner, right? So likewise, you can see volatile acidity is a significant variable. So it has provided this facility to, these are significant quotes, right? So in statistics, we used to measure it with confidence intervals, right? So significant evidence is this confidence interval has been set to these values, right? So if they are within these values, this 3 star means it tends up to the ideal scenario alpha equals 0, right? So likewise. So then with higher amount of stars, we can cross them with a higher amount comparatively, so that we can contribute them for the final model we are trying to prepare, right? Um, and these are corresponding z values, and these are corresponding probability values for the z, right? With the help of these probability values, we can make decisions whether these attributes are evidence or not, right? So this is a standard error. The standard error must be minimized, right? They are in large amounts when you train some models that cannot be trusted, right? We can prevent from making those type of models. So these are estimates, coefficients. So this is nothing else, this is the intersect, right? So how we can explain this model? I'll make you remember again. Let me hang over this. Let me check first of all whether it is being correct. Yeah, okay. Usually I used to do it right. Okay. Somehow here, um, let's say probability of color. Color equals one. I don't remember whatever that is. I think it must be red wine. Let me check this code again. We have done it almost, right? Already we have done up to this movement. We have created everything gradually from A to Z, right? So we have combined these two data sets and we have arranged them meaningfully. 1 0 assigned. Yeah, it was assigned. Red was given 1 and white was given 0, right? Okay. According to that, probability of color equals 1. Let me call it, let me say it is given by P, right? It is given by P. I don't know whatever the probability, I can find out the probability. It's given by little p, right? Then what's the other one? P C equals 0. P of C equals 0 is given by 1 minus p, right? So then, the ratio between them is known as odds. Odds is given by p over 1 minus p. Then we can make little p the subject when you cross it. We can say it's going to be equal to what? Um, let's go there, let's go there. Um, okay, odds over 1 plus this, right? It's given, little p is given by odds over 1 plus odds. And then uh, in advance, we have uh, implemented this little p. Little p is given by what? This is given by um, yeah, e to the power is given by e to the power beta node, that's e1 times x1, like that. You're having a couple of variables, right? Um, this becomes e to the power beta node. It's like this, right? You can see when x reaches up to infinity, I to the power infinity becomes infinity, then the denominator becomes infinity, right? Then when we take it out, we can cancel them off, and you can say it's going to be equal to 1, right? It's going to be equal to 1. Give me a few minutes. Yeah, really sorry for the inconvenience. I had to go out. Here we can conclude this likewise. So let me change the color. Right. We can conclude this likewise. B equals e to the power. Let me say it's e to the power z. right? Then e to the power z. We can divide both the denominator and numerator by e to the power z. Then we can rewrite it like this 1 over 1 plus e to the power minus z, right? Okay, then z is nothing else, it's given by beta naught plus beta 1 x1 plus beta 2 x2. Likewise, it is corresponding to a number of attributes we have contributed for the final model, right? So when z approaches to infinity with the help of limits, you can say e to the power minus infinity tends up to 0, then 1 over 1 equals 0, right? There is a limit, right? Because after immediately the Kolmogorov invention, Kolmogorov um, those axioms found by Kolmogorov, we have gone through limits and we have invented so many distributions nowadays, right? So we are working with them. This also is a model which is derived based on binomial probability distributions, right? So likewise, when z equals when z approaches to minus infinity, you can say this becomes e to the power positive infinity, then denominator becomes infinity, then 1 over infinity tends up to 0, right? Then the probability goes to 0. So that's how there are two boundaries as 0 and 1, right? So it's like that. These values are only up to these attributions and their values, right? Okay, so this is the mathematical background. Actually, I have explained that in advance. Then, when we substitute all these values in this equation, you can see it can be simplified up to this scenario. I'm not gonna do it again, right? But I will make you remember this, right? So, in my application, there are a couple of variables. There are when I contribute all these attributes for the model, there are 1, 2, 3, 6, 9, about 12 variables are there, right? Likewise, beta naught is nothing else, just minus 1 point. Beta naught is just minus 1.77 sorry, 717 p plus 3, right? It's nothing else, it's this one. This is the intercept, right? It takes beta naught and then corresponding beta 1 for the fixed acidity, right? Likewise, beta 1 times x1, likewise, you can continue it, right? Then you know that we can get the logarithm of both sides, then we can rewrite it as ln odds. It becomes beta naught plus beta 1 times x1 plus beta 2 times x2, likewise, right? So this is known as logic P, right? We used to call it logic P, right? Right, okay. So this is what we can find out with the help of binomial logistic regression model. Let me clean this, right? Right. Okay. So I have eliminated these insignificant, less significant attributes were eliminated in my model. We have done it last week, right? So then model evaluation, even model evaluation was done, right? Uh, this one we have eliminated those insignificant attributes, then we have contributed only significant attributes for that, right? It was named as M1, right? They were right, okay. Now you can see, we did it last week, right? Now you can see all these variables are significant, right? they are significant, they are highly significant, then only we can explain the entire model meaningfully with all these attributes, right? This is an evidence statistically, right? And now they are having their own coefficients, right? Then you can compare, for example, volatile acidity, standard error of volatile acidity in my the model when we have contributed to all these fixed acidity, sorry, volatile fixed acidity, right? 1.23 or 1.23. Yeah, it has been reduced, right? So likewise, in my earlier model when I trained the model contributing all the variables, it was around 1.23, but it has been reduced a little bit, right? Likewise, you can compare all these standard errors also, right? For making sure whether this is a better model or not. Actually, this is the best evidence, right? Not only that, we can see this AIC value. AIC value is 353, 353 here. Yeah, actually uh, it must be decreased for a better model, but here it has been increased a little bit. Can be happened likewise due to some density distributions. Some variables can be biased, so sometimes they can be overfitted, right? Due to them, those type of things can be happen. Somehow you can try some more models. I have shown you on the this combination, right? With the experiences on these attributes, you can check more, right? Then what we have to explain. Right, okay. There are some plots. I have explained them. It's nothing else, just inside plot function. Then you can include your model what you have prepared. Then these are model plots, right? What does it say? What does it say? Residual will speed up, right? Residual is nothing else. It's just predicted values and your predicted values and your uh, real observations, right? Real observations. So let's say your prediction is one, and your real value is one, and then it means that really there is a red wine, and my prediction is red wine. It is predicted as a red wine. That corresponding row with the help of the corresponding row and the when we let it go through the model, we could predict it as a red wine. When there is no difference, it is tallied almost, and the difference between them is just zero. It is known as the residual, right? Then the residual was predicted, right? So if it is free from errors, it must be exactly zero. You can see in this plot there are a couple of outliers. So uh, these outliers may these are um, not tallying with the prediction, right? These couple of points are not tallying with the prediction. That's why there is a deviation. So there are such points, couple of points are there, right? So due to this point, the accuracy of the model may be decreased a little bit, right? If there are some more points like that, if this is not lying, if most of these points are not lying along this y equals 0 axis, right? Y equals 0 means this x-axis means that it's not a better model, right? We cannot recommend, we cannot make sure that model. The thing is, we can get results through these functions, but if you do not have a better idea about the background of this mathematical intuition in minute able to explain it meaningfully. So you cannot make decisions, right? Decision making is impossible, right? Okay, it's fine. There are some deep sessions, so I hope to explain even them later. Here, the major thing is I want you to go through these codes and just understand it in my first level, right? That's my purpose. I want you to just understand this model and how to read these outputs and how to read these plots and how we can make decisions based on them, right? So here, this is for this is known as quantile residual, right? This is the actually this is stands for the normality of residuals, right? This explains how far it is normality of each of these residuals, right? It is assumed to be that when there is a linear regression in the linear regression for both linear regression and logistic regression, we do this, right? And it's an assumption. We assume that all these residuals must be normal, right? But in logistic regression, due to some reasons, it can be changed a little bit, right? But in linear regression, it must be like that. Most of the times, even this logistic regression, it must be a normal distribution. But here you can see there is a deviation between this dotted line and these points. Couple of some of these points are deviated, right? It means that these residuals are not normally distributed regarding these points, right? Okay, then scale location. Um, yeah, I did this for you. Even I can, I will share this with you. I will publish this on my website, right? Uh, so even in integration, we use this. Um, so it should have a actually it should have a random propagation around this dotted line, right? Random, it must be propagated because the variance of these residuals must be a constant, seem to be constant, right? The variance is seem to be a constant in linear regression and logistic regression. And then finally, leverage. Uh, it's an indicator, something about says something about outliers. Uh, these are called as outliers. These points are called as outliers. Then you can call these rows individual and just check them. Even you can eliminate them from the data set like this. Let me check them. What are these numbers? 1080, right? Was the data set I used? Wine, right? 1080. Wine, wine, square bracket, 1080. All these columns are needed, not only 1080, but also but also 1575. 1575. Thousand 1575. Uh, we have one more observation, right? We have one more observation. What is it? 4381, right? 4381. 4381. Uh, right. Okay, let's see. what are these roles? Uh, these uh, these roles has affected on these roles have affected on the final model badly. There is a this is an indicator. This leverage, Rachel leverage is an indicator of the influential cases, right? So it identifies these rows as outliers, and even we can run the same model by eliminating these rows, right? How we can check when will it happen. And let me call it a method, right? GLM. What are significant variables? Colors. Train. Train equals. Sorry. Data equals train, but we have taken on the we have eliminated these columns. What are they? What are they in my final model? 112, 10, 9, 112, 10, 9. It's 1, 12, 10, 9. 1, 9, 10, 12, right? And not only then, I wanna eliminate um, yeah let me check this. This is based on the train, therefore I have to eliminate them based on train, right? Actually these are not what I wanted, but it will not be included there. Then I'll use to put it here, right? Minus C. Let me copy this and paste on this. Right. Okay. Now let's take a look at the summary of the model. Right. Let me call this two. And let me show the plot ml to apply. Yeah, it is on it. Yeah, this is completed. Uh, we have to define the family, otherwise it will not be indicated as binomial logistic regression. Binomial, that's a pretty mistake I have made. Still, it is not executed. What's the yeah? Let me check. Data equals object. Uh, this has given us a result, right? There are some rows. I have eliminated these rows and these columns. What's wrong with it? Yeah, first of all, let me call it TR, right? TR, then let me change this TR. Okay, let's run it again. What's wrong with it? Colors object is not. Mm, GLM formula colors. So isn't there any attribution as color? Is color? Yeah, actually, there was a spelling mistake, right? I have named it as color. It's not colors. That's why it did not work. It's nothing else, right? I will exclude this, so I will put minus sign, right? Okay. Now it should be working well, right? Now it has indicated. Yeah, now these points have been replaced again. Though we have deleted those rows, they are replaced with other rows. Those are executed in our dataset, right? So likewise, we can identify what are the outliers. If they are irrelevant, we can eliminate them from the entire system, right? If it does not help, no need to bother about them. Just you can keep them in your model and just uh, then you can present your final model. And we have evaluated. So you have asked me to do this using this table. It's nothing else, just we can do the same with the help of table, but then we have to compute all these sensitivity, specificity, positive prediction values, and all of them must be computed then, right? Okay. With the help of predict function, last week we did it, right? Depending on this model, right? New dataset is picked as test. In order to test in this, we have split them into two parts. We can remember that, right? Type is response because it's a binomial logistic regression. Though it's a rich one, even you have to use them, right? So then the threshold value is 0.5. If else function is used, then 1 comma 0, right? Then right, I have attached them into the dataset, right? Let me show you. Even we can do it using table, 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 test set. I have color and I have uh, predicted color, right? Predicted colors. Test, right? So this is the confusion metric now, right? This is the confusion metric. You can see it over there. You can see it over there. It gives us the same result, right? Have not set seeds. This is sensitive for setting seeds when you randomly change the sample. The result can be changed, right? Right. Okay. If you try to change it frequently, if your result is changed with the higher amount, it means that in advance you have fitted um, model something biased, and we have to go for a better model, right? Should not be changed with higher amount. The accuracy should not be changed with higher amount, right? When you re-sampleize it, right? Okay. So what does this confusion matrix say? This is for, I'll use this one, right? This is for reference and this is for prediction, right? So this is my true value, right? This is a white wine, and according to my model, it is explained correctly. 969 white wines are explained correctly by the model, right? And 311 red wines are explained correctly in my model, right? So five red wines are identified as white wines according to my model. Here, what is it? So six here, right? Positive prediction value is nothing else. This is the metric. Um, when we say table, let me convert it into a metric. Con confuse as dot metrics. No, table. Keep the table, right? Uh, confuse confusion metric. 101 this is how we can compute the accuracy, right? 1 comma 1, right? Plus I have written it as confounds. It's not confounds, it should be confusion, right? Um, must be divided by summation of entire values, right? Confounds 4. Even we can use a loop here. I'll repeat it, right? 1 comma 1, 1 comma 2, 2 comma 1, and 2 comma, right? Okay, this is the accuracy, right? So likewise, you can predict positive prediction value, right? Means that in this model, according to the current library, with the help of confusion matrix function, we have made it last week, right? So it has designated a positive class by 0, right? So then 0 stands for the positive class, then positive prediction value. This proportion is 10, it is pretty close to 1. It is given by 969 over 969 plus 5, right? It's a prediction, positive prediction value. That's how it is given, right? So both of them must be pretty close to 0, sorry, pretty close to 1. And we can trust in both results, right? And it will affect on the final accuracy. Then couple value should be pretty close to 1. I'll talk about all these indicators later, right? These are significant indicators what we can use for explaining the entire model, right? So these are compulsory to be considered uh, when we explain binomial regression model, right? Okay, for now I think that's all. So if you try to just run this as a logic p. You know, logic p means ln of odds, right? Ln of odds. is given by e to the power, right? Ln of odds is given by beta node, this one, plus this one times this one, right? You can write it, right? And then check whether it is true or not, right? And you can get ln of odds corresponding to all these scenarios, right? So that's what given by this model, right? That's the duty of this model, right? Okay, for now I'll stop it by here. Today I discussed some of theory parts and what's the contribution for this final model. So we could identify these uh, mostly contributed for the final model, and the accuracy with the accuracy we can satisfy with the accuracy. That's a pretty good accuracy, right? You can we could make the prediction with a high accuracy. If I'm given a wine bottle, then I can predict based on these attributes. If I know these values, then I can let them go through this model and I can predict whether that's red wine or white wine, right? Okay, thank you very much. Now I'll stop it by here, right? So next time, I hope to come with rate regression and inelastic regression, right? Both of them will be discussed continuously with no stop, right? So keep touching with it, right? Okay, bye.